So first off, what is a confidence interval? A confidence interval is a range computed using sample statistics to estimate an unknown population parameter with a stated level of confidence. We're going to talk about that more later, but just to get you started off, that's the definition of a confidence interval. All right, so to start off, sampling distributions are distribution of sample statistics with a mean approximately equal to the mean in the original distribution and a standard deviation known as standard error. So an important aspect of sampling distributions is the standard error, which is actually just the standard deviation of the sampling distribution. You can use StatKey to find the standard error of the sampling distribution as well. So sampling distribution is what we're going to be using to find the confidence intervals. There's a way to find confidence intervals of a sampling distribution, which is what we're going to focus on mostly today. So sample size has a huge impact on standard error in a sampling distribution. They have an inverse relationship, so a larger sample size would make a smaller standard error. So vice versa, a smaller sample size would mean there's a larger standard error. And then a large sample size will make a distribution more normal. So if there's a distribution that only has, say, 20 cases in it, or if n equals 20 and it's left skewed, it will be less left skewed but more normal. It will still be left skewed, but it'll be more centered towards the middle of the distribution if there were more participants or if there's a larger sample size. So confidence intervals. So these can get kind of confusing, so you just want to pay attention and take it sort of one step at a time. So again, it's a range computed using sample statistics to estimate an unknown population parameter with a stated level of confidence. So the biggest keyword there, I would say, is population parameter. With confidence intervals, you do use the sample statistic to estimate, but in the end, you're making an estimate about a population parameter. So any conclusion you're going to make from a confidence interval, you'll be using a population parameter. So you always want to be speaking in terms of the population. So the formula for a confidence interval is the sample statistic plus or minus margin of error. And margin of error is just a certain multiplier times the standard error, which we already talked about earlier. Standard error is similar to standard deviation of a sampling distribution. So the margin of error depends on two factors. So the level of confidence, which affects the multiplier, and then the value of the standard error. So those two things affect the margin of error. So the way, if you're wondering what the multiplier is, so you'll be asked to determine, say, a 95% confidence interval, and we already discussed earlier in the semester the empirical rule, and this is the chart we use to talk about the empirical rule. And basically, you just identify the multiplier from the empirical rule, so this is how it's going to be every time. This will stay consistent. So I highlighted 95% because that's the one that you use most often. You'll find times when you may use a different number like 90, 99.7, 68. But 95 is most common. That multiplier I think it's 1.96, but we just rounded up to 2. So in that case, if you were having to find a 95% confidence interval, your multiplier would be 2 times the standard error. So the multiplier is just based on the empirical rule, as you can see, based on what percent level of confidence you want. And then a common form for 95% confidence interval, which you'll see most of the time through the semester, is confidence interval is equal to the sample statistic plus or minus 2 times the standard error. That should say 2 times. My apologies, that should say 2 times the standard error. I'll fix that here. 2. So that'll be the format for a confidence interval. It'll be the sample statistic plus or minus 2 times standard error. Okay, next. So Another important thing when you're talking about confidence intervals is you're going to get your final answer as two numbers, because the formula, as if we go back, the formula, is plus or minus. So you're going to get two numbers, one from subtraction and one from addition. So you're going to get an interval. So that'll be your numeric answer, but you want to make sure that you also write a conclusion statement interpreting your data, which is just as important, I think. So it'll look something like this. I am, if you say 95% confident, sure that the population proportion of Penn State students who have dogs, for example, is between 1.6 and 2.7. So that's an example of that. This is just the consistent format for it. You definitely want to make sure that you use the population parameter always. Do not use the sample statistics, any symbols like that, any symbols that represent a sample. You always want to speak in terms of the population with confidence intervals. So here's just an example. I just want to walk through one before we do a review question. It makes it much easier to just walk through it. So at the beginning of the spring 2017 semester, a representative sample of 501 Stat 200 students were surveyed and asked if they owned a dog. The sample proportion was 0.559. There's a standard error of 0.022. We can use this information to construct a 95% confidence interval for the proportion of all Stat 200 students who own a dog. So here, when we go back to our formula, confidence interval equals sample statistic plus or minus margin of error. We're given, we see a sample statistic of 501 Stat 200 students. So that'll be used to represent our sample statistic. And then since we're looking for a 95% confidence interval, our multiplier would be 2. And then 2 times the standard error is 0.022. So remember, margin of error is the multiplier times standard error. So in this case, it would be 2 times 0.022. And once we add all that out, we add it and subtract it out, we get 0.515 and 0.603. You could see it in the top form or the bottom form. Sometimes you write it with brackets. I don't think it really makes a difference. And then you can make a conclusion statement about it. Say, I am 95% confident that the population proportion of Stat 200 students who own a dog is between 0.515 and 0.603. So remember, we use the population proportion in our concluding statement. We always want to speak in terms of the population for that. All right, so bootstrapping. So bootstrapping is a little bit different from sampling. This can kind of get confusing. There's just like a few rules for it, and as long as you know the rules, it should be pretty simple to understand. So bootstrapping is a resampling procedure that uses data from one sample to generate a sampling distribution by repeatedly taking samples from the known sample. So it's called sampling with replacement. So the example I like to use for this is if you say that you have a bunch of numbers like in a hat or something, and you pick out one number. So the numbers would be from an original group of data, and you just throw them all in a hat. You pick out one number, and you can record that, and then you throw it back in a hat. So that number has an equal chance of being picked. Just because it's picked once, it can be picked again. So as long as you have the same values from your original sample, it can be picked again. In addition, another rule is that you have the n must be the same for the bootstrapping. So if you have an original sample size of 15, your bootstrap sample must have a sample size of 15 as well. So an example that will help kind of put that into perspective is we have a data concerning the heights of individuals in a random sample of n equals 15. To construct a bootstrap distribution for the mean height, we would first randomly select one individual from that sample and record their height. Then, with that individual placed back into the sample, we would randomly select a second individual and record that height. So because we pick the first individual, we would put them back into the sample, so we could easily pick them again at another point. Just because they're picked once, they could be picked again, or a third time or a fourth time, as long as it doesn't go over 15, because that is our original sample size. So that's called sampling with replacement, because you put each case back into the sample after recording the original piece of data. And then you repeat that process until you select 15 values, or whatever your n equals. So you don't want to go over n or under n, you want to keep n the same. So we use those 15 values to compute a bootstrapped sample mean. And then you just repeat that process several times. So some things to take note of here, individuals can appear in the bootstrap sample more than once. That's very important. Just because you see a number only once in the original sample, you could see that number several more times in the bootstrap sample. And then the distribution of many bootstrap sample means is known as the bootstrap distribution, or the bootstrap sampling distribution. So similar to the other sampling distribution, this one is called bootstrap sampling distribution. Okay, so then once we have our bootstrap sample, we can create bootstrap confidence intervals similar to what we did before. It's different though. So there's two ways to do this. Sorry, I don't know why it says one and one. The first way to do it is standard deviation is, so the standard deviation is the standard error when you construct a bootstrap confidence interval. So you would just use sample statistic plus or minus 2 times standard error. That would be the formula for a 95% confidence interval. If it was any other confidence interval percentage, you would just change the multiplier. So it would just be changing the 2. And then you can find the middle 95% bootstrap statistics if you're doing a 95% confidence interval. This is called the percentile method. It's actually preferred because it works regardless of the shape of the sampling distribution, and it's very easy to do when you're using it in StatKey as well. So I think I have a StatKey example on here. So another important thing is the impact of sample size on your confidence intervals. So just they have an inverse relationship. So as sample size increases, the standard error will decrease. I show that in these two charts here. The charts show, I think it was how many students own dogs as before, and they have the same proportion. So in the one on the left, the sample size is 20, and it says there's a sample of 20 students, 12 own a dog, and that p-hat would be 0.60. The same p-hat for the right, a sample of 200 students and 120 said they own a dog, so they have the same proportion. So now you can clearly see that the proportion doesn't have effect on the standard error, it's the sample size. So in addition, the confidence intervals between the two disappear. You can see on the bottom that the confidence interval for the distribution with the smaller sample size on the left has a much wider confidence interval than the one on the right, because we're not using, if you think about it, we're not using as many people, and our data is not as reliable. It's not as representative of the population as a whole. But if you're surveying more people, you will have more representative data, therefore your confidence interval will be smaller. So the narrower your confidence interval, the more accurate per se, or the more sure you are that that your estimate is correct. All right, so we're going into our first review actually. So the first one is constructing a 95% confidence interval in a random sample of 525 Penn State World Campus students. The mean height was 67.009 inches with a standard deviation of 4.42 inches. The standard error was computed to be 0.195. Construct a 95% confidence interval for the mean height of all Penn State World Campus students. So take a few seconds, minutes, go over that, think that through. Use the formula that I had a few slides before, and type your answer in the chat box when you're done. Okay, let's go over this. So the answer is A. So referring back to the formula, confidence interval equals sample to statistic plus or minus margin of error. Remember, margin of error is just 2 times the standard error. So I think I threw one of the options out there that use the standard deviation. I think that looks like B. B, I use the standard deviation instead of the standard error. So you want to make sure that you use the standard error definitely. And then C, I think C was just adding the standard error without using the multiplier. So you want to make sure you use the multiplier. It's kind of confusing sometimes with the margin of error being used, and then you have to remember that that's another separate formula because you won't be given just the margin of error. You have to remember that you have to calculate it. And then once you get the margin of error, you just add and subtract that to the sample statistic, which was 67.009 inches. Okay, any questions on that? I'll move on to the next question if there aren't any questions. Okay, so the next question is a bootstrap sample. So remember, I'll just review some of the things I said before. So here, this is a question that says, which of the following sets of data could result in a bootstrap sample from the given sets of values? So as before, I mentioned that the bootstrap sample cannot be over or under n, it must equal n. It can use repeat values from the original sample, but it cannot use values outside of the original sample. So go ahead, take a few seconds, think that over. If you get an answer, type it in the chat box. I'll go over it soon. Yay, good. C is the answer. So with A does have 10 values in it, but some of the values are not from the original distribution. 3 is not in there, 4 is not in the original distribution. That's good job. And then B has 8 values, but I think the values are from the original distribution, but the N is different. So good job on that. All right, and the last review. So this is just a sample size question. So I discussed earlier the relationship between sample size and standard error. So based on that, which bootstrap distribution has a smaller standard error? All right, awesome. Yes, B does have the smaller standard error because remember, as the sample size increases, the standard error decreases, or as the sample size decreases, the standard error increases. They have an inverse relationship. So awesome. There wasn't much tonight, so that is it. Thank you guys for coming. I know the Super Bowl